Hello, and welcome to our exercise session for Federated Learning Assignment 4. In this assignment, you will know the basic idea of decision tree and be able to implement the FL network using non-parametric local models, for example, the decision tree. First is dataset. We use the same dataset as we used in assignment 3. So we use the FMI data 2025, and it includes some stations and the names and coordinates and its temperature data. And we also use the same methods to build a FMI network. Yeah. So next we introduce FED relaxed. In assignment 3, we learned about the linear model, but we know that sometimes linear model is not really convincing. So we introduce this feather relaxed. The basic idea of feather relaxed is we assume that for each node I, its neighborhood already have optimal weights. So as we see here, in each node I, we assume that its neighbor already have its optimal weights, so it's fixed. So we can update each neighbor using this equation, because this W hat I prime is its neighbor, and we assume it's known. And this AII prime here is adjacent matrix, and the alpha is a hyperparameter. So we can solve this equation relatively easily. Any questions so far? Okay. So next come with the non-parametric models. So still we look back to our GTV minimization. The idea of GTV minimization or the idea of better learning is if two datasets or two individuals or two nodes, if they are closely related, then they will have similar models. But how can we say two models are similar? How can we measure their discrepancy? Well, in the GTV minimization, we use this graph penalty. We calculate the Euclidean distance between their weights or parameters. But what if we don't have parameters? Recall that a function in a computer science field is something that, for example, this is a function. A function in computer science is something that takes input and gives some output. If we can collect all this input and all this output, then we can define this function, right? So if two functions, they are similar, then given the same input, they should also have the similar output. And based on this idea, we introduce this federated relaxism with agnostic model. This D here means the discrepancy between model HI and HI prime. And we unfold this equation to write this D as loss function. We have this equation here. The L with X and HI X is a loss function for each I prime with dataset X and HI, where the X is feature as we used. And this HI is prediction from its neighbors. So with this dataset, and we use this dataset on H prime, it can measure the distance between HI and HI prime. Our next task is we take decision tree for example, because we cannot get the parameter from decision tree. So you can see in this picture, first we build some public data sets. This public data set corresponding to this data set here. And it's unlabeled, means it only have a feature. So in node I, we use this public data set as feature. Then how about label? The label is prediction from his neighborhood nodes. We use the prediction from its neighbor as label. And this is the new data for node I. And we combine this new data with this original data. We have this augmented dataset. And we use this augmented dataset to train node I. And because we also have some information from its neighbor, which is labeled here. So in this way, we can compare the model for node I and node I prime. Any question here? Okay. For task, first you need to initialize the model for each node, which is a decision tree model. And then you need to build this augmented dataset, use xpublic we give here. And then you need to use xlocal and xpublic, combine them together as augmented dataset. Then use this augmented dataset to train each model in each node. Any question? Okay, we have a question here for the public dataset. Well, first, the idea to compare to agnostic model is because we don't have their parameters, so we cannot compare their parameters to different models. How can we compare these two models without knowing their parameters? We can only use data. Because this is federated learning, we need to care about privacy, so we cannot share our data directly. So we build some public data. In this code, we build the public data according to highest temperature and the lowest temperature from our whole data set. We only use highest temperature and the lowest temperature. So this data set will not leak privacy for each node, right? So this public data is safe for each node. And using this public data, we train on each node. For example, we train this public data on node I. Then we get some label from, if we train this public data for node I prime, then we get some label from I prime. Then we have the whole data set with feature and label. and we use this public data and label from node I prime to train node I. Then we can compare the discrepancy between node I and node I prime. Okay, our next question. In Federated Learning, we are assuming that all nodes have updated weights. In Federated Relaxed, oh no, here. Okay. In Federated Relaxed, in each iteration of each node, we assume that its neighbor have fixed weights. We should here. The head here means it's optimal. We assume it's optimal, but it's not necessarily optimal. But for node I, we assume that its neighbor have optimal weights, so we can fix it. Then we only need to care about the node for the weights for node I. Then it's ideal Jacobian metric, Jacobian algorithm, if you know it from linear algebra, is that we fix other parameters and we can by this way we can only update this wi here. Did I make it clear? Okay, thank you. Okay, our next question is our next question is what we are augmenting in non-perfect model. Okay. What we are augmenting data because we use public data and the label from neighbors to build a new data set. And we add this new data set to our original data set. So this original and the public data set is augmented data set. So it's like a data augmentation, but using a label from neighbors. Any more questions? Maybe I can explain again how we use this augmented data set and how do we compare to agnostic model. If we think the model is a function, how can we compare two functions? In GTV minimization, if these functions have same structures and we know their parameters, for example, if it's a linear model and we know its width and bias, then we can directly compare the parameters. That's the discrepancy between two models. But what if our model is agnostic, means we don't know its parameter? Then if we take the function as some input to output, if two functions, if they are similar, then given the same input to different functions, then their output should also be similar, right? Then we can measure the discrepancy between two functions by their output. So the difference between output of function x and output of function t. And this is the discrepancy between the t. And the x here, because we cannot directly share our data with our neighbors, so we need to build some public data. We denote as x public. which is here in this image. And using this public data for each node I and node I prime. For example, this is F I, this is I prime with the same X public data. And next. And let's have output. SC Y prime. And then this L output. Let's see Y. And we compare the discrimination between Y and the Y prime. And how can we compare the discriminancy between Y and Y prime? The Y is labeled, right? It's labeled for public data sets. For example, Y here is labeled for public data sets using and Y prime is labeled for public data using F prime. So if we train X public and Y on S prime, and we train X public Y prime on F, and in F prime, the loss function will be loss with X public and Y, right? Because this label corresponds here, this label, and this is a prediction of F prime. And also same for F. The loss function is trained on X public, and this is label for F here, right? And if you know the LP norm for functions, it looks like this. This is the same idea as we used using this augmented data, right? Because it's T here. We integrate this discrepancy in the domain D, and the domain we used in our model is this X public dataset. No question. Why we are doing no parametric local model? Because we want to generalize this GTV minimization. You see that in this GTV minimization, we assume that we have this W here, which is weight or parameter for model. But some model, it we don't have access to the parameter. For example, decision tree here, we usually don't have access to the parameter for decision tree, but we still want to do the federated learning. So we need to compare two models. But if we don't have these parameters, then how can we compare these two models? That's why we use this model agnostic federated learning. So the reason is because not all models have the parametric that we can compare using this method. Another example is if two nodes, for example, this node and this node, they use different models. For example, this node using linear regression and this model using some neural network. Then we cannot compare their with using this Euclidean node. Okay, next question. Um, all model does not have same parameters for the reason. Yes. One reason is if we know their parameters, but different model have different structure, then we cannot compare their parameter using this Euclidean node. And if for some reason we don't know their parameters, then we can only compare them using data, which is a method we introduce here. We build some augmented data using this augmented data to compare models. Okay, we have a question. Um, how do I receive neighbors from G? That's yes, you can use which there must some function from network X that you can acquire every neighbors for every node. I don't remember it exactly, but there must be a function can directly get the neighbors for nodes. And, by the way, speaking of discrepancy, do you know how to compare some like other mathematic objects? Uh, for example, um, how do we compare two vectors? We can use dot product. How to compare two strings? We can use Hamming distance or edit distance. How do we compare two probabilities? One method is using KL divergence. And how can we compare, for example, matrix space? We can use Hausdorff distance. And also for functions, use LP form. And I feel the discrepancy or distance between two objects is a really fundamental concept in machine learning. For example, if we take this, for example, uh, to compare vectors, we use dot product. And this is a method used in attention mechanism. If you read this paper and then know about attention and transformer, how do we know uh, which context we should pay attention to? If we live in a vector space, then can compare their dot product. And for example, this one, if we use probability machine learning, if we assume our model is some kind of distribution, then using prior and likelihood, uh, for some reason, we don't want our distribution too wild. We don't want our distribution goes too far from our prior. So we can use scale divergence to constrain our model, to constrain our search space for distribution. We have a question here. The question is, sometimes the local dataset have 8 values and sometimes have 10. Uh, in dataset, each dataset, you can see that each local always have 10 raw data. And if we do this print test split here, it's here. If we use this train test split using test size is 0.2, then we have 8 train datasets and 2 test datasets. That's why we have 8. But the whole dataset is always 10 for each node. And for those, if you not really familiar with Jacobian algorithm, or optimization problem. Imagine we have an optimization problem, and it has many, many parameters. For example, W1, W2, W3 to Wn. We have many, many unknown parameters for this optimization problem. So for some reason, we cannot update all these parameters simultaneously. It might be too much computation or simply nothing or simply impossible sometimes. Then how can we do that? For example, in W3, we update one parameter by fixing other parameters. For example, if we want to update W3, then we fix other parameters. And we can only update one parameter, and it becomes relatively easy. And after some iteration, for example, this W3 gets its optimal solution. Then we can update other parameters. For example, W1 here. When we update W1, we also assume that other parameters are fixed. Then we can only update W1 until it gets its optimal here. And that's how we using this Federated to update our parameter in each node.